Hello everyone and welcome to OneClass. My name is Jeff Krause. I have a PhD in physical chemistry and today I'm going to run through a few undergraduate upper high school level physics questions. So here's our first one. Okay, so we have a regular hexagon of side 10 centimeters. And there's a charge of 5 microcoulombs on each vertex. See if I can't draw this regular hexagon here. So there's a 5 microcoulomb charge. And this side length is 5 centimeters. And it wants the potential at the center of the hexagon. So these are actually all equilateral triangles. So this distance here is also 5 centimeters. Sorry, not 5, 10. So this distance here is 10 centimeters, which we're going to need because the potential for a point charge is 1 over 4 pi epsilon naught Q over R, where R is our distance. So that means that for one of the charges, the potential at the center is just going to be 1 over 4 pi epsilon naught 5 times 10 to the minus 6 coulombs over 0.10 meters, which is 10 centimeters in meters. Now, for the 6 charges, all we need to do is just sum it up. And the nice thing about the potential is because it's not a vector quantity, we can literally just add them. So and there's no there's no variable here that we're really incrementing over, so we just multiply by 6 basically. And so, and putting in some value, and so using E naught as 8.854, 18782 times 10 to the minus 12, and that would be in coulombs per volts meter. Our potential comes out to be 2.387 times 10 to the minus 5 volts. If we check, kitty here coming to visit. If we check the solution here, it looks like we're doing the same calculation, so I'm not certain why our values differ. So I might just double check. Yeah, so maybe mine is just funny. Pi divided by 8.854. It looks like it's just the differing value of, oh no. I did something wrong there. But yeah, it looks like I made a mistake in copying. So it looks like it should be 2.696 times 10 to the minus 5 volts. My apologies. So that was that was my calculator there. So that looks okay then. Alright, so now the next one here, we have a simple one. So it's just we have an ideal gas with a volume of 1.6 centimeters cubed. T equals 20 degrees Celsius. Which is equal to 293.15 Kelvin. So that's just adding 273.15. And at atmospheric pressure, so our pressure is 101.325 times 10 to the 3 pascals. So our volume is, multiply this by 1 times 10 to the minus 2 centimeters per meter cubed. So that's 1.6 times 10 to the minus 6 meters cubed. Alright, so it wants us just to determine the number of moles. So so PV equals nRT. Rearranging this, we get N is PV over RT, which is 101.325 times 10 to the 3 pascals times our volume, 1.6 times 10 to the minus 6 meters cubed, over our gas constant, which for this I'm using 8.314, and this is in pascals meters cubed per mole Kelvin. And the temperature is 293.15 Kelvin. Okay, so we can see our units cancel here, giving us 6.6518 times 10 to the minus 5 moles. Okay, and then it wants to know the number of molecules. So the number of molecules would be this value times Avogadro's number. So 6.6518 times 10 to the minus 5 moles times 6.022 times 10 to the 23 1 over moles, which gives us 4.006 times 10 to the 19 molecules. Okay, so molecules isn't a real unit, so that's why the value is unitless. Alright, so looking at the solution here, we get about the same number of moles. The difference there would be probably my extra digits on the pressure and my extra digits on the temperature. Okay, and then the number of moles would be multiplication by Avogadro's number. They get 3.99 times 10 to the 13, which looks like a calculator error to me, just because it should be roughly around the same range as if you add up the exponents here. So 23 plus 5 minus 5 is 18. Obviously is going to move depending on how these guys multiply. So it should be 18, 19, not 13. So I think there was a calculator mistake there. So 4 times 10 to the 19. Mostly correct, just a small mistake at that point. Okay. So here we have a figure which shows the total acceleration of a particle moving clockwise. So we've got a circle moving with some velocity v and some acceleration a with a radius of 2.5 meters, and this is a 30-degree angle. Okay, so we've got a 30-degree angle in here. That is our A. Okay. For this instant of time, find the radial acceleration, the speed of the particle, and its tangential acceleration. Okay. So the radial acceleration would be the amount that's along R. I don't know why I wrote it like that. So this would be its radial acceleration, and this would be its tangential acceleration. So its radial acceleration is just a cosine of 30 degrees, and its tangential is a sine 30 degrees. So then A radial is this A cos 30. So A is given in the question as 15 meters per second squared times the cosine of 30, which comes out to be 12.99 meters per second squared. And its tangential acceleration is just, I don't know why I put that there, is just our A times sine of 30, which comes out to be 7.5 meters per second squared. All right, so I kind of skipped a step and did A and C, but that's okay. Now the speed of the particle. So recall that our radial acceleration is related to our tangential velocity. As this. So then our tangential velocity is the square root of AR R, which is, we already solved as times 2.5 meters, which is 5.70 meters per second. Okay. So we can get its tangential, its radial, and then we know, so the tangential acceleration, or the tangential velocity is related to the radial acceleration, not the tangential acceleration. So that's a mistake there. So there in C, the velocity or speed is related to the radial acceleration, not the tangential acceleration. I presume that's the reason why the question was laid out this way, to get you to do the radial then the speed. So it was kind of a hint. So let's do that. Okay, a system is in equilibrium. We've got a hinge point here, a strut, a mass, okay, and then that guy's at theta, and then this is coming out at phi. And the question wants the tension in the cable. So I'm going to go ahead and put my tension this way, because this is my mg force from this. And the strut itself is 45 kilograms. And then phi is 30 degrees, theta is 45 degrees, and it wants the tension in the cable and both the horizontal and vertical components of the force on the strut from the hinge. So this guy is applying forces in both directions. So I'm going to call this FHY and FHX. Okay, so we've got a few forces here on this hinge. So to get these, we're going to need the tension. But to get the tension, so if we try to use that our sum of forces is 0, that's going to be tricky. But we can use the sum of torques using this as a hinge point. So our sum of torques must also be 0 because we're in equilibrium. So let's go through and figure out each of the torques. So for our tension, our torque is going to be our tension cross our R, which is tension R sine theta, or sine, I use gamma here. Now to figure out the angle that we are referring to, we put the vectors tail to tail here. Oops. So let's do this. Like this. So our tension kind of points out this way, and our R points out this way. And now just to relate them to some angles that are in the question here so we can figure things out. So we've got alright, so that's our phi. That's our theta there. This angle in here is 180 minus theta. And so this angle up here must be, I'm just extending this out. Yeah, just extending this out. So this angle and this angle are the same. This angle up here is 180 minus theta minus phi, which is equal to theta minus phi. So that makes that theta minus phi, and it makes that 180. Can't see what I'm doing, you. Oh, torque. All right. That makes that 180 minus theta minus theta minus phi, sorry. Okay, so then this equals, so these 180s are going to cancel, theta minus phi, which equals minus theta minus phi, so phi plus phi. Makes sense. So this angle in here is just phi. So this is actually a similar triangle here. Which means, finally, that this angle, so our gamma angle, which is the full angle, that's the difference between the two, is 180 minus theta plus phi. Ooh, okay. And then the sine of 180 minus theta plus phi is just the sine of minus theta plus phi, which is the sine of theta minus phi. All right, done. Okay, so that's a gamma there. So this is T R sine of theta minus phi. And now we need to assign a direction if we're going to do it this way. So we're going to use right-hand rule. So that means put your fingers in the direction of the force. Put your fingers in the direction of the force. Your palm in the direction of where the angle is going to go to the R. So that would be your palm going on that side, and then your thumb points in the direction of the torque. And so our thumb points into the page, and I'm going to have the into the page be the negative direction for torque. And so our torque, finally, for our tension, is just TR sine theta minus phi, and we can put in some values here, and TR sine of 15 degrees. And actually, instead of R, I should have used, does it say how long the, does it say how long the strut is? I guess I use L actually for the length of the strut. So L, L, L. So I'll just use L for the length of the strut, and that'll just come in later. Okay, so there's our tension. It took a while, but it's okay. So our mg force for the strut. This one I should have said. So not the 225 kilogram. Our tension is now mg cross r. I'm just putting kind of a vector symbol over the whole thing, which is a little inappropriate, but that's okay. So there's our strut. There's our mg force. Now this one should be significantly easier, as this angle here is our theta. And so we can see that mg, and it's applying to L over 2. Right, so it's half the length, so mg L over 2. And I'm going to use gamma again for this angle because I'm just going to use that for each one of my torques. And we can see that our gamma angle this time is 90 plus theta. So this equals mg L over 2 sine of 90 plus theta, which is just mg L over 2 cos theta. Okay, again we can put in values and call this mg L over 2 cosine of 45. Very intrigued by this. Okay. And then our last torque is our 225 kg torque. 225 kg torque. So our torque is 225 kilograms times G. I'm just putting that in just so that we know where it is. It's going to sit at L and sine gamma. So there's our 225 kg times G. And again, this angle is going to be the same as our previous one. So it'll be 90 plus theta. And we know that this is going to give us a cos. So it's pretty much the same. Oh yeah, and I forgot, should have done the right hand rule here. So our fingers point in the direction of the force, our palm in the direction of L, and our thumb points straight up, meaning these are both positive torques. Okay, so there's my 3 torques. So now my sum of torques is from my tension, which is minus T L, and that was sine of 15, plus my mass of my strut, which was 45 kilograms, times my G, 9.8 meters per second squared, times the cosine of 45, and then plus my 225 kilograms times 9.8 meters per second squared, times the cosine of 45. And so we can, and this all equals 0, so we can rearrange this for the tension. So we can see, and these, sorry, I should have had an L over 2 there and an L here. We can see we can cancel our L's. And so we can rearrange for our tension as 45 kilograms times 9.8 meters per second squared times the cosine of 45 over 2 plus 225 times 9.8 times the cosine of 45 all over the sine of 15 degrees. So running this through our calculator, we get 6,626.5891 newtons. I'm just using a fairly large number of significant figures there to make sure I don't miss anything. And now just double checking here. So just for part A, so again, we're just using sum of torques. And for sine, we had sine of 15. They use sine of 45, which is not correct. But the funny thing is, sine of 45 equals cos of 45, so it doesn't matter. Which is why the numbers come out the same. So that's okay. Okay, so then we want to solve for, so now that we have our tension, we want to solve for our horizontal and vertical forces. So for B, we have F net equals 0. So some of our forces in our X, if we look at our diagram again, or maybe I'll just redraw it in retrospect. So we have our strut, we have our tension, we have our 225 kilogram, we have our 45 kilogram, and then we have our hinge forces in the X and the Y. Okay? And we already figured out that this angle here is phi. So we can break down our tension by looking at that angle. So we've got, this is a 30-degree angle, and this will be T cos 30, and this will be T sine 30. And so then, now if we look at our X direction, our sum of our Fx is just our hinge force minus our T cos theta, cos of 30 degrees. And so then our hinge force in the X direction is just our tension times the cosine of 30, which comes out to 5738.79 newtons. Okay? And then if we look in our Y direction for C, we have a few forces. So we have our hinge Y, we have our mg for our struts, so 45 kilograms times 9.8 meters per second squared. Our mg for the 225 kilograms is from our tension, so our minus t sine 30. I might as well put t in there instead of all the other values in. 6626.589 times the sine of 30. So we can rearrange for our Fy hinge, and that would be 59.29 newtons. And so there's our x and y components of our hinge forces. If we check through the solution here, so it's about 57.40, so that looks good, and about 59.60, so that looks good as well. Okay, so used sine 45 instead of cos 45 in A. No numerical difference in this problem, but would be for other angles. Yep. Still is mostly correct though. Okay, so now we've got a box sliding down a 38.5 degree ramp. Okay. Okay, so there's our 38.5 degrees. The acceleration of gravity is 9.8. Determine the coefficient of kinetic friction between the box and the ramp. All right, this is two questions here. So we've got our friction, we've got our normal, and we've got our mg. For this question, it's going to be easier to just define my x direction as down the ramp and my y direction as up this way. If we draw our perpendicular, then this here is our 38.5 degrees. So our mg force here can be decomposed into mg cos 38.5 and mg sine 38.5. And to give them some direction here, right, there's going to be pointed down and pointed down. So if we look at our sum of forces in the y, this equals our normal force minus our mg cosine of 38.5 degrees, which equals 0 as the box isn't moving up or down in our y direction. So our normal is just mg cosine of 38.5. Okay, and now if we look at our x direction and using our friction force is mu n, so it's mu mg cosine of 38.5. Our sum of x forces is our going in the positive x direction is our mg sine 38.5. And we're going to subtract our friction, which is mu mg cosine of 38.5. And this equals our MA. And we're given in the question that the acceleration is 1.39 meters per second squared, and we're asked to solve for our mu. So first of all, we can cancel all our masses and divide out g. So we have that mu, and then rearrange here. So we have mu g cosine of 38.5 is equal to ax minus g sine of 38.5, or dividing the whole thing by that factor to have mu on its own. We have that our mu is, that was my mistake here. It should be minus a. So mu is sine of 38.5 minus a over g, all over the cosine of 38.5, which comes out to 6, if we 225 minus 1.39 over 9.8. Both of these are meters per second squared. And we can see that these units will cancel. All over 0.7826. Running this on our calculator, we get 0.6142. So there's our coefficient of kinetic friction for the ramp. If we check the solution just for this first part, then it looks good, 0.614. Okay, so going back up to the second question that we're given here. So we have a 1 kilogram block, an 8 kilogram block, and a 6 kilogram block, all on a table without friction, and we push it from the left and we push it from the right. So FL equals 11 newtons, FR equals 8 newtons, and it wants to know what is the force of the 8 kilogram block, or what is the force on the 8 kilogram block by the 6 kilogram block. Okay. So first of all, let's treat the whole system as its entirety. So that would be a mass of 8 plus 6 is 14 plus 1 is 15. And we've got our FL and our FR. And so then our F net is 11 newtons in the positive direction, so I'm going to use that as my positive x and that as my y, minus 8 newtons in the negative, so that's 3 newtons total. So the acceleration of my system is m. So F net is ma, so 3 newtons is equal to 15 kilograms times my acceleration, which means that my acceleration is 3 over 15, which comes out to be 0.2 meters per second squared. So we can get all of our net forces now on our individual blocks, as they're all traveling with this same acceleration. So for the and we can not only get our nets, so F net for our 1 kilogram is equal to 1 kg times 0.2 meters per second squared, which comes out to be 0.2 newtons. our F net for our 8 kilogram block is 8 kilograms times 0.2, which is 1.6 newtons, and our F net for our 6 kg block is 6 kg times 0.2 meters per second squared, which is 1.2 newtons. Okay. So those are our individual forces on those blocks. Now we can decompose our 8 kilogram block to figure out, so it's going to get a force from the 6 kilogram block, which I'm going to call F6 kg, and a force from the 1 kg block, which I'm going to call F1 kg. And so F6 kg is what we're looking for, and F1 kg we could find, but it's easier if we look at our 6 kilogram block, because it has a force from the right and a force from the 8 kilogram block. And I'll end up messing it up if I if I use this kind of terminology too much, but we know from Newton's third law that our F8 kg here is equal to minus our F of our 6 kg. So we can get our force of our 6 kg by solving for this F8 kg. So our F net on our 6 kg block is F8 kg minus Fr, which is equal to this 1.2 newtons. And so our F8 kg, our force from the right we know is 8 newtons. And so that equals this 1.2. And so our force from our 8 kg block is 9.2 newtons. Which makes sense, as to get that acceleration we need to surmount that right force. And so that means that our F6 kg is minus 9.2 newtons. So that's the force that the 6 kilogram block is applying to the 8 kilogram block. Okay. So if we check our solution here, so we solve for acceleration, we can get each of our individual F nets. Use Newton's third, and then it just takes it as they just take it as a fraction, which doesn't work here, because if the force of our 8 on our 6 or our 6 on our 8 was only 1.2 newtons, it wouldn't actually surpass the force from the right, and then the 6 kilogram block would actually be moving backwards, which is impossible. So error in second question. Should be 9.2 newtons, not 1.2. Okay. Okay, so now we have 3 points on an equilateral triangle. I'm going to try to draw this as well as possible. So Q1, Q2, Q3. Each are 5 meters away from each other. And these angles are all 60 degrees. Okay. We're given that Q1 is 6 times 10 to the minus 9 coulombs. Q2 is minus 2 times 10 to the minus 9 coulombs. And Q3 is 5 times 10 to the minus 9 coulombs. And we're asked to solve for the resultant force on Q3. So our force is a vector quantity, and it's 1 over 4 pi epsilon naught Q1 Q2 over R12 squared times R12 hat. So a unit vector in the direction of R12, or alternatively we can write it as and use the vector R12. Okay, so now to solve for the resultant force, we need the individual forces. So, and to do that, we need the vectors as well. So let's go ahead and define an axis system here, where this is our x and this is our y. And I'm going to define each of the position vectors. So our 3 vector is going to be the more tricky one to do. But we can see that it's, if we draw the triangle from the origin out, this is 5 meters, this is 60 degrees. So this is 5 sine 60, and this is 5 cos 60. 5 sine 60 is 4.33 centimeters. So I did everything in centimeters, but it's all in meters. Okay, I'm just going to have to convert, which is, and this is 2.5 meters. So our 3 here is 2.5 meters in the I hat, so the x direction, plus 4.33 meters in the j hat direction. Now, our total R is still going to be, or our R3 is just 5 meters. And our R2 is pretty simple, so it's just going to be 5 meters in the I hat, and our R1 is the easiest one, is just 0. So now our R31 vector is just R3 minus R1, and this points in the direction of R3 of Q3 from Q1. So this is the force on Q3. Okay. And so this is 2.5 meters I hat plus 4.33 meters j hat, minus 0, so that's easy. And then R32, so again pointing in the direction of R3 from R2, is now 2.5 meters I hat plus 4.33 minus 5 meters I hat minus 2.5 meters I hat. And now our R31 is just the magnitude of R31 vector, which is 5 meters, and our magnitude of R32 is just 5 meters. So now we have everything in place to compute our forces. So our force on 3 from 1 is 1 over 4 pi epsilon naught times our charges, so 6 times 10 to the minus 9 coulombs, times our Q3, 5 times 10 to the minus 9 coulombs, over our 5 meters squared, times our cubed, times our 2.5 meters I hat, plus 4.33 meters j hat. This is going to, using an epsilon naught of 8.85, 418782 times 10 to the minus 12. Then our F31 comes out to be, now I'm just going to recalculate a bit because I messed up a little bit on my units here. So 1 over 4 pi epsilon naught times 6x9 minus 9 times 5x minus 9. And did I mess that up too? No, okay, good. And divided by 5 cubed. So this should be 2.157 times 10 to the minus 9 newtons per meter. So if we do the units out there, it'll be about newtons per meter. I should have said this was seconds squared, coulomb squared per kilogram meters cubed. Okay. And so this is all multiplied by our 2.5 meters I hat plus our 4.33 meters j hat. And so then this will come out to be 5.3925 times 10 to the minus 9 newtons plus 9.3399 times 10 to the minus 9 newtons j hat I hat. Okay, and then so that's our F31, our F32, is then going to be 1 over 4 pi epsilon naught. Our charge on 2, so minus 2 times 10 to the minus 9 coulombs, 5 times 10 to the minus 9 coulombs, over our 5 meters cubed, times our minus 2.5 meters, plus our 4.33 meters j hat. Okay, and so this is going to be minus 7.198 times 10 to the minus so 3 went to 9, so 4 goes to 10 newtons per meter times our minus 2.5 plus our 4.33. And so that used the same E naught as I used above, obviously. And so then here we're going to get so the minuses will cancel, so 1.7975 times 10 to the minus 9 newtons I hat, and minus 3.1133 times 10 to the minus 9 newtons j hat. Okay. And so then our net force is just the sum of these two. So our net force on the 3 particle is just the sum of our 2 forces, which is, just to rewrite them here, that should be minus, sorry, minus 3.1133. There we go. And so then our net force is 7.1900 times 10 to the minus 9 plus 6.2266. And then if we want the magnitude, that's just the square root of the component squared. As so. Oops. Figure that's probably visible, but I'm just going to clean it up a bit. There you go. Which comes out to be 9.5114 times 10 to the minus 9 newtons. Okay. And about 9.4, 9.5, that would be just differences in rounding. And using 9 times 10 to the 9 for K instead of epsilon naught. Would also do that, so that looks good. Okay. I'm just going to take a quick drink. So we've got at 37 meters below the surface, we let out an air bubble, and the temperature is 5 degrees Celsius, and the volume is 0.2 liters, which is 0.2 decimeters cubed. So for this, we're going to add 273.15 to give us 278.15 Kelvin. And we're going to go ahead and multiply this by 1 times 10 to the minus 3 meters cubed per decimeter cubed, which is 0.2 times 10 to the minus 3 meters cubed. Okay, and it wants to know what the volume of the bubble is when it's reached the surface, where it has a temperature of 25 degrees Celsius, which we're going to add 273.15 to get 298.15 Kelvin. Okay. And the pressure, so the pressure at the surface is going to be 101.325 times 10 to the 3 pascals. And the pressure here is going to be 101.325 times 10 to the 3 pascals plus rho GH, where H is our height. So we're given the density as 1025 kilograms per meters cubed times 9.8 meters per second squared times our H, which is 37 meters. Remember, a Pascal is a Newton per meter squared, which is what this is going to give us. So the units of Pascal works. And so if we do this math out, then we get 472.990 times 10 to the 3 pascals. Okay, so there's our initial pressure volume. So we've got PV equals nRT. So then nR is PV over T. It's just easier to solve for both N and R together because both of them will stay constant. And so we can put in our values, 472.990, don't forget my units. That's in pascals. My unit's 0.2 times 10 to the minus 3 meters cubed. So that's my volume. And my temperature is 278.15 Kelvin. And this comes out to be 0.340097 Pascal meters cubed per Kelvin. And now when my bubble reaches the surface, I have PV equals nRT again. And I'm solving for my volume, so I can rearrange as volume is nRT over P, which is going to be my nR factor here. Times my temperature, which I solved out as 298.15. And my pressure, which is 101.325 Pascal. Canceling some units. Then we're going to get a meter cubed unit, which is a volume, so that's good. And if we do out all these numbers, we get 1.001 times 10 to the minus 3 meters cubed, which we can multiply by a liter per 1 times 10 to the minus 3 meters cubed. And so we get 1.00 liters. So our volume of our bubble at the very top is exactly 1 liter. And if we check through the solution here, that's what they got. So that looks good. All right. Okay, so now we're asked to find the current in the 4 ohm resistor. Alright, so we've got a multiple battery situation here. And I'm going to just apply Kirchhoff's loop laws. Oops. Here. And this battery is 3 volts, 6 volts, 9 volts. I wish there was a way to like rotate this without. Oh, okay. 2 ohms, 8 ohms, and 4 ohms. So this is the one we were interested in. The loop I'm going to draw, or the loops I should say, so I'll start with this one. I'm also going to assume that current runs in this direction. So that'll be my first Kirchhoff loop. Now it's easier to remember the signage here if we call the little guy a 0 and the big guy a 3. And so going from 0 to 3 is a gain of plus 3 volts. And then we're dropping I1 across our 2 ohm resistor. Is that what I did? I don't want to do, well, okay, there it is there, okay. We're dropping, we've got our current 1, which is being dropped across our 2 ohm resistor here. And then we're coming down here and gaining another 6 volts as we go across this guy. And then we're going to drop some I2 across this 4 ohm resistor. Okay, and then we're going to be back at the beginning of our loop. So now for our second loop, I'm going to draw this one. There. And so now I've got, so our first loop, for our second loop, we've got 3 volts minus our I1 times our 2 ohms. And now we're dropping a third current across the 8 ohm resistor. And we're going from 9 to 0, so we're dropping 9 volts across that battery. And these should both equal 0, I should have said. And so then there's our 2 loops. Now to solve for our individual currents, we also need I1 is our total current. So I1 is equal to I2 plus I3 in this case. And so then we can say that, and because we're solving for our I2, so that's the one we want, then we might as well express it as I3 is I1 minus I2. And I'm just doing that to try to eliminate I3 as fast as possible. So then if we take the second equation down here, then this becomes 3 minus 9 is minus 6 volts minus I1 times 2 ohms. I'm just dropping some of the decimals here that are unnecessary. I1 minus I2 times 8 ohms equals 0. Minus 6 volts. 8 and 2 is minus 10 I1. And we're going to end up with a plus 8 ohms I2 equals 0. So we can solve now for our I1 in terms of our I2. So we can bring the I1 to the other side and then divide it all by 10. So I1 is minus 6 volts over 10 ohms plus 8 ohms over 10 ohms I2. Okay? And now we can plug this into our first equation. So our first equation was, just to rewrite it here, minus 6 volts minus I1. Was it minus 6 volts? No, it was 6 volts plus 3 volts is 9 volts, so plus 9 volts. Minus I1 times 2 ohms. I'm just going to draw it not quite so 2 ohms times I1 minus 8 ohms. Minus 4 ohms times I2 equals 0. Getting myself all mixed up here. Yeah, okay. So that was our first equation, and so we can plug in our I1 into there. So 9 volts minus 2 ohms times minus 6 volts over 10 ohms plus 8 ohms over 10 ohms. Actually, we can cancel our ohm units there. Minus 4 ohms times I2 equals 0. Okay, so now that we have this, we can collect some terms here. So we've got 9 plus 6 over 5, so this becomes a plus, and they're all in volts. Minus 8 over 5 ohms I2, and then minus 4 ohms I2 equals 0. We can now pull our I2 to the other side and rearrange, and so then I2 is 9 plus 6 over 5 volts over 4 plus 8 over 5 ohms, which is 10.2 volts over 5.6 ohms, which is 1.821 amps. So then I2 is 1.821 amps, and that's the current through the 4 ohm resistor. So that's our current. Checking through our solution here. So we want to use a couple Kirchhoff loops, and then we get 1.821 amps. So that looks good. Okay, so here we've got an ice chest, which contains 12 cans of soda at 4 degrees Celsius. So we've got our 12 cans of soda. I'm not going to be able to draw, but whatever. Alright, so the mass here is 12 times 0.3 kilograms. The temperature is 4 degrees Celsius, and our heat capacity is 3,500 joules per kilogram degrees Celsius. And now we drop a watermelon in. That's my watermelon. The mass is 6.4 kilograms. The temperature is 29 degrees Celsius, and the heat capacity is 4184 joules per kilogram degrees Celsius. It's just the same as water, they say. So that's what it'll be. And then it wants to know what the final temperature of the system is. Well, they're in thermal equilibrium, and we're assuming it's a sealed system, so our delta H total is going to be 0. Our delta H for our cans is going to be MC delta T, which is our mass of our cans, our heat capacity, TF minus TI. And actually that's going to be delta H for both our watermelon and our cans, or at least the general expression. So our delta H total, so I'm just going to get rid of cans here, is just the sum of our delta H for our cans and our watermelon, and that equals 0. So our delta H cans is M, the mass is 12 times 0.3 kilograms. Heat capacity is 3,500 joules per kilogram degrees Celsius. And it's TF minus 4 degrees Celsius. And then we add the delta H for watermelon, which is 6.4 kilograms times 4184 joules per kilogram degrees Celsius times TF minus 29 degrees Celsius. Okay, and that all equals 0. So now we can collect terms in TF and move the rest to the other side. So this will be 12 times 0.3 kilograms times 3,500 joules per kilogram degrees Celsius plus 6.4 kilograms, 4184 joules per kilogram degrees Celsius, TF. And that has to equal 12 times 0.3 kilograms times 3,500 joules per kilogram degrees Celsius times 4 degrees Celsius plus 6.4 kilograms times 4184 joules per kilogram degrees Celsius times 29 degrees Celsius. So if we calculate these values, this comes out to be 39377.6 joules per degree Celsius TF is equal to 826,950.4 joules, or TF is equal to 21 degrees Celsius. Okay, so we check the solution here. I wouldn't say that's close enough to be within. So trying to figure out why that would be. I can't really see a reason. Looks like a calculator error though. It could be a calculator on our end though. So it's worth it to kind of rationalize this through. So our total mass of our cans is about 3.6 kilograms, which is about half the mass, a bit over half the mass of our watermelon. The watermelon is also about 4/3 the heat capacity. So we would expect the temperature to be closer to the watermelon. But it isn't that far away. It shouldn't be only a 2-degree difference. I would expect that the heat that it would be, because 29 minus 4 is 25 degrees Celsius. So I would expect it to be a bit closer to the 29, but probably close to like 2/5 the temperature difference probably. So at least a temperature drop of about 10, which is what we found. So I assume I did it correctly, and that this person made an error. Okay, so this is another Kirchhoff loop question, and it's asking what is the current in each resistor So we've got, now I'm just assuming, although it's not really sketched out like here on the question, that they must match up or link up, otherwise I'm not certain how to do it. So there's 15 ohms, 12 ohms, and 20 ohms. And this is R1, R2, and R3. Okay, so one thing that I will note here is when doing a Kirchhoff loop question, you do want to not only assume the direction of current, but make sure that all the loops start and stop at the same position or the same point. So mine are starting from this top right corner and ending back up at the top right corner. So there's going to be my two loops here. That should be sufficient to get all these. So if I do my first loop, so this is 12 volts, this is 9 volts. So my first loop, I'm going to start here. I gain 12 volts, and then I lose I1 times 15 ohms, and then I come around and I lose an I2 times 12 ohms, and then I lose 9 volts. Okay? And then for my second loop, I gain 12 volts, I lose my I1 times my 15 ohms, I come all the way down here, I lose I3 times 20 ohms, and then I come back to 0. Okay. And then my current is splitting at this split point, and so my I1 is equal to my I2 plus my I3. In this question, it doesn't matter. I'm solving for all three currents, so I need all three of them. So I'm just going to, first of all, make sure that I am following along. And I believe I am. Okay. So then I'm going to use I2 is I1 minus I3 to simplify. So I'm going to put this into my second equation. So my second equation becomes 12 volts minus I1 times 15 ohms. No, I'm not going to put it in my second equation because that doesn't make any sense. Sorry. I guess I'm going to put it into my first equation. Sorry. So my first equation, not my second. Okay, so my first equation, first of all, I'm going to remove that 9 volts. So 3 volts minus I1 times 15 ohms minus I2 times 12 ohms equals 0. So then it becomes 3 volts minus 15 I1. I'm just moving that to the front so that it's a bit less in the way. I1 minus I3 equals 0. And this becomes 3 volts minus, so minus 15 minus 12 is minus 27. And then plus 12 ohms I3 equals 0. Okay? And now my second equation is 12 volts minus 15 I1 minus 20 I3 equals 0. And I'm going to go ahead and actually multiply this whole thing by 5/3, actually by minus 5/3. And the reason I'm going to do that, and the reason I can do that, is because it all equals 0. But this is going to turn my first equation into 5 volts minus 45 ohm I1. Minus 5 volts plus minus 20 ohms I3 equals 0. And then I think it's fairly obvious why I did that now, because I'm going to take 1 and I'm going to minus 2. So I'm going to take 1 and I'm going to subtract 2. So I get minus 5 minus 12. I'm going to take 2 and minus 1. That makes more sense. And so I'm going to get 12 minus a minus 5, which is plus 17. I'm going to get minus 15 minus a 45, which is minus 60. And then the 20s here will cancel. And so then my I1 is just 17 volts over 60 ohms, which is 0.2833 amps. Okay, so now that I've got my I1, I can plug that into either equation to get my I3. So I'm going to use my second equation. So I've got 12 volts minus 15 ohms times, I'm just going to use 17 volts over 60 ohms because that way I don't have any rounding issues, minus 20 I3 equals 0. So now I can rearrange this and say that I3 is 7.75 volts over 20 ohms, which is 0.3875 amps. And then now my I2 from above is I1 minus I3, which is 0.2833 amps minus 0.3875 amps, which is minus 0.1042 amps. Okay. So there's my I2. That's the same I3, and that's the same I1. Okay. So just as a note as well, I1 and I3 came out positive, meaning that the current direction I assumed in my Kirchhoff loop was correct, whereas I2 comes out negative, meaning that this current actually goes this way. Or the current I assumed was the wrong direction, so the current actually travels this way in this circuit, or in this line. Whereas the other two, the directions were as appropriate. Okay, so this looks good. So solution is correct. All right, so a small breather question, fairly simple one. So we've got a bar, horizontal bar, with a pivot point, and so that's 25 centimeters, that's 75 centimeters. We're given that the force on this end is 10 newtons, the force on this end is 8 newtons, and it asks what is the net torque. So torque is F cross R. So the torque due to the 10 Newton force is 10 newtons, which we can decompose this into FR sine theta, where theta is the angle between them. So R here is 0.75 meters. And if we line the force and the R vector up tail to tail, we see that it's 90 degrees. Sine of 90 degrees is 1. We need a directionality though, so we point our fingers, for the right hand rule, we point our fingers in the direction of the force, our palm in the direction of the angle to breach the R vector, and then our thumb points in the direction of the torque. So in this case, it's inside into the page, and so I will actually call this a negative torque. So this should be a negative. So this would be minus 7.5 Newton meters. So our torque to our 8 Newton force is 8 Newtons cross with our R, so times our 0.25 meters. And again, we have our force, we have our R vector, and we use the right hand rule by pointing our fingers in the direction of the force, our palm in the direction that goes towards R, and our thumb points in the direction of the force. And in this case, it's out of the page, which I'm defining as a positive torque. So this is 2 Newton meters. And I'll give it a K hat just to keep them straight, which also means that these are vector quantities now. And so then our net torque is minus 7.5 Newton meters K hat plus 2 Newton meters K hat, which is minus 5.5 Newton meters K hat. So there's my net torque. Checking the solution here. We do indeed get 5.5. They didn't bother with the directions, but it's in a counterclockwise, so negative torque would invoke a counterclockwise direction, at least the way I've defined it here. So that looks good. All right, we've got a bullet shot into a piece of plastic. A plastic block, and it penetrates the block by 0.4 meters. So the initial speed of the bullet is 490 meters per second. Our VF here is 0. And so what is the magnitude of the acceleration as it's penetrating the block? And assume that the force or the acceleration is constant. So in this case, we've got VF equals VI plus AT. So our acceleration can be written as minus 490 over t meters per second. That's our VF is 0. So that we can write our acceleration that way, but we really only have a displacement. So our displacement can be written as this. And again, we're missing a time. Our xi we're defining to be 0. So we can define a time, or we could have solved for time here instead. What did I do? Okay, yeah. So we have 0.4 meters is equal to our initial velocity, so 490 meters per second, times our time. plus 1/2 minus 490 meters per second over our time times our time squared. So that's going to cancel one of those. And so our 0.54 meters is equal to 490 meters per second minus 1/2 of 490 meters per second times our time. And so we can solve for our time as 0.4 meters over 245 meters per second, which is equal to, apparently I didn't bother solving for that. Okay, so then our acceleration is minus 490 meters per second over our time, which we can write as minus 490 meters per second over 0.4 over 245. Which this flips around, so this would just be 490 times 245 all over 0.4, which is minus 300,125 meters per second squared. And so then the magnitude of our acceleration is the unsigned value, which is just 300,125 meters per second squared. Okay, so we check the solution. That is indeed what was found. So that is correct. Okay. If we approximate the mass of the moon as 1/80th that of the Earth, and assume it has the same density, what is its diameter? So if we say that the mass of the moon is 1/80th the mass of Earth, well, the mass of Earth is the density times the volume of Earth, which, if we assume the Earth is spherical, is 4/3 pi r cubed, where r is the radius of the Earth. Okay. We can say the same thing about the moon. So the mass of the moon is rho times the volume of the moon, which is rho times 4/3 pi times the radius of the moon cubed. Now the mass of the moon is 1/80 times the mass of Earth, which is then rho, which is then 1/80 rho times 4/3 pi radius of Earth cubed. So we can then equate these two to say that rho times 4/3 pi radius of the moon cubed is 1/80 rho 4/3 pi radius of the Earth cubed. So a bunch of these can be canceled if we assume the same density. Get rid of 4/3 pi. And so then the radius of the moon cubed is about 1/80th the radius of Earth cubed. And so then, using the radius of Earth as 6,378 kilometers, then the radius of the moon is 6,378 kilometers over 80 to the 1/3, so the cubed root of 80, which comes out to be 1480.2 kilometers, or the diameter would be 2 times the radius, which comes to be 2960.4. If we look this up, if we quickly Google this, it comes out to be about 3,500 kilometers, so not a bad assumption there. And of course we made a few assumptions that it was spherical and whatnot. Okay, so looking at the solution here, g is the acceleration due to gravity. So g over g is a constant, and m over r squared is a constant, but the problem with this solution is that g over g is not necessarily the same constant for all planets or for all objects. So in fact, if we wanted to go this route, saying that g is gm over r squared for the Earth and for the Moon, if we set these two equal, then we're saying that the gravitational acceleration on the Moon and the Earth is the same, which is just not true. So we could use the fact that we could use the difference in the gravitational acceleration, but that wouldn't work. And in fact, we can see this doesn't work because the diameter comes out to be half the actual diameter of the Moon. Information due to gravity on the Moon is not this. On the Moon's surface, I should say, is not the same as for Earth, which this assumes. Okay. So here we've got a resistor constructed from a cylinder. And it's of length L. And we want to find the resistance between RA and RB. And the current is actually flowing radially outward. Okay, so if we look at how we define resistance as the resistivity times the length over the area, in a usual wire, we have our current going this way, so this would be our length, and this cross-sectional area would be our area. Now we have these shells, so I'm going to actually redraw this rather than mess it up too much. And my redrawing is going to be terrible. We have these shells that we're calculating our current over. So our current, if I redraw this, so if I imagine some length dr, which is at a distance r from the center, and I have my full length, if I unroll that into a sheet, then I have a width of 2 pi r and a length, or a width of L and a length of 2 pi r. So my area is 2 pi r L. And if we look at this from the side, or visualize it from another angle, my current, or at least what the question is saying, is my current is flowing through this length, and my length here is dr. So my little increment of resistivity is just rho dr over 2 pi r L. right? So my increment of resistivity is just my current is flowing through this sheet, which has a length or a thickness of dr and an area of 2 pi r over L. So to get my total resistivity for the entire surface, I need to integrate this expression from RA to RB. So I take my rho dr over 2 pi RL, which is rho over 2 pi L integral RA to RB of dr over R. Integral of 1 over R is ln from RA to RB, which is rho over 2 pi L ln R. Oops, sorry, I did that. Ln RB minus ln RA. And we can combine this because when you subtract lns, you can divide what's inside there. So it'd be RB over RA. And so then that would be my full resistance. Okay, so so we do need to integrate. So they used R for the length, pi r squared as the radius, or the pi r squared L as the radius. So I don't agree with that because, again, if we look at our little picture here, it doesn't make any sense to me that this side length would be pi r squared. Yeah, that doesn't really make any sense to me. And I think it's overdoing it. And so I think we've got a factor of 2 different in the end. And so I think the area, so the initial integration assumes incorrect areas should be a factor of 2 1/2. So I believe that's okay. Okay, so we've got Colonel John P. Stapp studied whether a jet pilot could survive. He rode a rocket-propelled sled that moved down a track at 632 miles per hour, and he brought it to rest in 1.4 seconds. We need to determine the acceleration he experienced. So first of all, I'm going to just bring this into kilometers per, or meters per second. So a mile is 1.60934 kilometers. So 632 miles per hour is 1017.10288 kilometers per hour. And then we're going to multiply this by 1 times 10 to the minus 3 meters per kilometer, and by 1 hour per 3,600 seconds, which gives us 282.52958 meters per second. Okay, so now our VF is 0. Our VI is this 282.5 meters per second. Oops. So our acceleration is just VF minus VI over T, which is minus 282.5 meters per second, over 1.4 seconds, which is minus 201.806 meters per second squared. Also, they want the distance traveled during this acceleration. So xf is vit plus 1/2 at squared, which is equal to 282.5 meters per second times this 1.4 seconds plus the acceleration times 1.4 seconds squared, which comes out to be 197.77 meters. So he travels almost 200 meters in decelerating. So our acceleration is minus 201, and our distance traveled is about 198. Any differences there would be rounding, it looks like. So that looks good. Okay, and I'll do this one. All right, so we've got a capacitance circuit here, in which initially we've got this connected. So this is, and we're given that this is 10 volts. This guy is 10 microfarads. And these are not connected. Okay. And we're given that this is 3 microfarads and this is 2 microfarads. Okay, so initially when just this is connected, and we're asked what is the final charges on these 3 capacitors. So initially when just this is connected, our capacitance is our charge over our voltage. So that means that our charge is our 10 microfarads times our 10 volts, which is 100 microcoulombs. And then after this gets charged, we switch this so they're no longer connected by a voltage. And so then now this charge flows across the 3 capacitors, basically. So we first need to figure out what the net capacitance is here. So our C2, our 1 over our C23 is 1 over C2 plus 1 over C3, sorry. So for capacitors in series, this is how we add them. So this is 1 over 3 microfarads plus 1 over 2 microfarads. So our C23 comes out to be 1.2 microfarads. And so the circuit, the equivalent circuit we have then is this, where this is 1.2 microfarads, this is 10 microfarads. And now our charge on both plates can be found from these expressions, but we don't know what our new potential is necessarily. But what we do know is that the sum of our charge should be 100 microcoulombs. So that means we know that the voltages should be equal. So we know that Q1 over C1 is equal to Q23 over C23. So they will reach equilibrium where the voltages are equal. And so we get this expression, but also our charge should be maintained. And so then we can solve for the charge on Q1 by rearranging this as so. So then we can say that Q1 onto C23 over C1 plus 1 is equal to 100 microcoulombs, or Q1 is equal to 100 microcoulombs over 1.2 over 10 plus 1, which is equal to 89.29 microcoulombs. So I'll say right here that we could have, because of this, the way the factors work out here, this is actually just the ratio of, if we work this out right, this is just the ratio of the total capacitance to the individual capacitance. And so there's likely a shortcut here. So now we can solve for our voltage. So now we can either solve for our Q23 directly as 100 minus 89.29, which is 10.71 microcoulombs. And we can also say that our voltage here is 10.71 microcoulombs over 1.2 microfarads, which is 8.93 volts. Now, because the charge on Q1 is this 89.29 microcoulombs, the charge on 2 is the same 10.71 microcoulombs, and the charge on 3 is also 10.71 microcoulombs. And so how that makes sense is that in closing the switch here, we get charge flow or flow of the potential for equilibration, and then it flows from this plate to this plate and back around. So that means that we transfer 10.71 microcoulombs here, pushing 10.71 microcoulombs off of this guy to here. So although it only transfers 10.71 microcoulombs, or there's only a net difference of 10.71, the other 10.71 comes from the adjacent plate. Okay. And if we check the solution here, this person just used the ratios, as I said. So you could just use the capacitance ratios to get that the charge is 89.29 and the charge on 2 is 10.71. And the charge on 3 will also be 10.71. So this is good. And I'm actually going to stop this here now. I'd say thank you all for listening. If you enjoyed this, please subscribe to OneClass. If you want to leave questions, please follow the links below the videos. This has been Jeff Krause for OneClass, and I hope to see you again.